Sorry. Yeah, so our class is now being recorded, and yeah, it's 10:30. So let me start sharing my screen. Okay, so my screen should be visible now. Hopefully the audio is fine, and we are set for the class to start. Okay, just one second. Yeah. Okay, so welcome to class number 13 of our course on Network Fundamentals for Cloud. Till last class, we have been discussing the single site data center network, where we've looked at the different protocols involved and how the data center network evolved from access aggregation core topology to a class topology, and how the protocols and the technology evolved from STP to Trill to VXLAN, where we are now. We also looked at the control plane of the VXLAN protocol last time. So with that, we actually got a fair understanding of how data center networks operate. Today, we'll look at the topic of multi-site data center networking, starting with um, the requirements for multi-site data center. Why do we need it? What are the use cases which require multi-site data center networking? We will see one of the most common use cases of multi-site data center network by looking at a case study, which is the looking at an example, not really a case study, but an example of a content delivery network that uh, is driven by the multi-site data center networking idea. And then we'll look at, so we'll summarize very quickly what, for the requirements that we've identified, what kind of protocols are most suited to support multi-site data centers. Okay, so that's the agenda for today. Hopefully we'll complete this topic in one class itself, because most of the things that we've learned so far, we will be reusing a lot of those protocols, technology, concepts in this. So why do we need multi-site data center networks? The need arises primarily from three distinct reasons. One is the requirement for having distributed redundancy. So in the subsequent slides, of course, we'll differentiate between local redundancy, which we sometimes also call as network redundancy, from geographical redundancy, which means that we are creating a geographically distant data center as a redundant data center for the primary data center. So both of them, we are clubbing them under distributed redundancy, saying that the data centers operate in a redundant manner, right? So it basically enables continuity of services in case one of the data center network services were to go down because of different reasons. So that's the first and foremost and most important requirement which tenants of data center or tenants of cloud networks typically have. I want redundancy in offering my services. Now, because I have redundant data center networks, I can of course use them as in an active standby mode where the redundant data center is completely standby. But I could also run them in active model, which means they are redundant, 1:1 redundant, but both of them are simultaneously handling the load. And if one of them goes down, at least the services will continue to operate with half the capacity. So that is where load sharing comes in. We say that the two data centers are actually sharing the load amongst themselves, and therefore together they are offering larger capacity to run certain services as opposed to what a single site data center would have been able to offer. Okay, so when we talked about class topologies and we talked about scalability, we said that while class networks can scale, and I can use the existing infrastructure to scale the network, but there is an upper limit to where we can scale, and that upper limit will eventually get reached when I have no more space in the data center itself. And of course, when the number of ports on the switches will also get exhausted, I have no other ways to expand that network. And in such case, it makes sense to expand in units of data center itself, have a multi-site data center where the two data centers together can load share and handle the overall service traffic, which a single data center is unable to handle. Now, when we have such load sharing data centers, it's also pretty obvious that if there are subscribers which are distributed across the globe, then I should direct the subscribers to the nearest data center, which will be able to give the best service, best quality of service to this subscriber based in terms of the delay, the error rate, right? So it overall improves the user experience. So essentially, we are saying there are multiple reasons. They all stem from the need to expand. But when we expand, we can achieve redundancy, we can achieve load sharing, we can also improve user experience by using the closest data center to service a subscriber. Arup, you post. Oh, okay. There was a question from Gautam. I didn't see that. Screen sharing going on. I'm not able to see. Okay, yeah. So Arup's posted it visible, I assume, for others. So Gautam, just try to rejoin if it's a local issue. Okay, Tanya can't hear me also. Gautam can hear, Tanya can't hear, but okay. Let me reshare once. Maybe I'll just stop sharing and share again. Okay, it's fine for you, Raj. Let me just type to Tanya that fine for others. Yeah, anyway, I'll just stop sharing and reshare once in case it helps. Okay, I've stopped sharing. Let me just share again. Okay, I'm sharing again. Hopefully it works. Okay, Tanya is able to hear. Gautam is able to see. So I think all good. We can continue. So yeah, for Gautam, yeah, for you and Tanya who couldn't hear, we were talking about the need for multi-site data center networks, and we listed three key reasons for having multi-site data center network. One uh, is distributed redundancy. These two sides of a data center act in a redundant fashion. They can, if one goes down, the other can take the load of the service. They can also operate in load sharing, active-active configuration, where the two of them share the service traffic amongst themselves. And the third is where when we have multi-site data center networks and their subscribers spread across the globe, in order to help improve the user experience, we direct a subscriber to the nearest data center so that he can get the lowest latency, the best throughput, and therefore a good user experience. So these are reasons why we will see that the overlay networks that we create for tenants often spread across multi-site data centers. Okay. So we'll look at these use cases, the service scenarios for multi-site data centers. We'll look at the first one, which is, as I said, the service network or the overlay network spreading across multiple data centers. I'm calling it the cross data center service deployment model. So we'll see why this is necessary, or why this is useful. We'll talk about redundancy, but first we'll talk about geographical. Maybe first we'll actually talk about network level distributed redundancy, and then we'll talk about geographical redundancy, using a geographically distant site for redundancy. And lastly, we'll talk about the user experience part by seeing how what we call as distributed cloudification. We are distributing the cloud across multi-site data centers and therefore providing service to subscribers from the closest location. So let's look at all of these scenarios one by one and see how the deployment changes across these use cases. So the first one is where you have a pretty elaborate or complex application that is implemented as a set of subsystems, and these could be hundreds of subsystems, right? Very complex modern applications that we see today would be huge. I mean, they could actually consist of these hundreds of subsystems. So it's possible that a single data center doesn't have the infrastructure or the capacity to host the entire application in totality. So not all the subsystems of the application can be accommodated on a single data center. It's also possible to be the case when you have private data centers and private cloud networks where enterprises have their own in-premise data centers. So it's possible that if I have offices across three geographical regions, I have an office in Hyderabad, Bangalore, and Delhi NCR. The data center, that infrastructure that I have within each of these offices, none of them is capable enough to accommodate my large-sized application. But put together the data center infrastructure that I have across all these three offices, it is sufficient to host the application. So what kind of a deployment architecture will I see in that case? I will have an overlay network that I am creating to host my application. But that overlay network, or VPC in AWS terminology, will spread across all these multi-site data centers. So in this diagram, we are seeing the three locations. We can continue the same example. This is Hyderabad, this is Bangalore, and this is NCR. And there are the three data centers that the organization has. And across all the three data centers, I've used the infrastructure to deploy my overlay network, my VPC. And in this example, I've just simplified. I've used three subsystems. I'm saying, let's say it's a web application. So web applications are known to have three tiered architecture. They have the web tier, the app tier, and the data tier. And because in this convenient example that I've taken, there are three data centers, I've conveniently mapped each of these three tiers of the web application to each of the data centers. So the web tier can run on data center one. Of course, there are multiple instances of the web tier running to handle the load, incoming load. The app tier could completely run on data center 2. The DB tier could completely run on data center 3. So the different subsystems of the application are deployed across the different data centers. And together, these three data centers are providing the physical infrastructure required to run that complex modern application. So what do we need in this case? We need, we know that the external traffic always reaches the web tier. The web tier is the entry point for any north-south traffic coming from outside the application, the internet. And then the web tier is only supposed to talk to the app tier and vice versa. The app tier is supposed to talk to the database tier and vice versa. So this is the communication channel that we need. External connectivity to the web to application bidirectional connectivity, app to database bidirectional connectivity. So essentially, we need interworking capabilities between these data centers to ensure that the interaction across the service layers, across the tiers, can be maintained. Right? That's our primary requirement in the cross data center service deployment model. So that's the first use case. The second, as I said, is more to bring in redundancy. Right? So we are calling it distributed redundancy, but I can have redundancy at the network level where I may even have co-located data centers in the same geographical region, but I'm still providing redundancy because they're two different sites. I can even have geographical redundancy where the standby site or the geographically redundant site could be geographically distant. So we'll come to that. First, let's look at the network level DR or distributed redundancy. So this kind of a model is better, often used for applications that are implemented using cluster software. So we know modern applications are once again not capable to be run on a single server machine. So we use a cluster of machines where you have some kind of a cluster middleware, a cluster controller, and that cluster controller controls all the servers within the cluster. The application, it may not be like we saw in the first example where the subsystems of the application were distributed. It is possible that every node in the cluster runs the same instance of the application, but together the cluster is able to provide me higher throughput computing. Okay, so this is typically what you will follow in a Hadoop kind of a architecture, or a map reduce kind of a map reduce kind of architecture, where I have multiple backend servers in a cluster solving the same problem and solving parts of the problem and contributing to solving the big problem. So when you have such cluster based deployment, the servers within the cluster, they need to appear to the external world as one entity. The entire cluster is like a high throughput server machine. Rather than having one huge server, I've actually taken multiple servers and put them into a cluster, and it has a huge capacity of compute. So all these servers in the network, which are, as I said earlier, they are typically managed by some kind of a cluster software or a cluster middleware. Right? They will appear as a logical server to the rest of the network. So essentially, for that, they will expose only a single virtual IP address to the external world. That's the IP address the external world will use to communicate with this huge cluster server. But the servers in the cluster, they don't need to be restricted to be within a single data center. And by distributing the servers in the cluster across data centers, I can actually achieve redundancy. One data center goes down, my capacity, throughput capacity of the cluster goes down, but it does not go to zero. So for redundancy purposes, I can distribute my servers in the same cluster across multiple data centers. So if you look at these diagrams, there are both ways that I can do that. I can actually use an active standby redundant model, or I can use an active-active model with network level distributed redundancy. What do I mean by network level distributed redundancy? Let's look at the first example. This is active standby model. So in the active standby model, the virtual IP address is bound to the primary data center's infrastructure, which means the routing in the internet has been set up in such a fashion that all traffic destined to the virtual IP will always arrive at the primary data center. None of it which will reach the standby data center. So I'm calling it active standby because one of the data centers is active, the other is standby from the perspective of external traffic termination. Right? All the external traffic comes to the active gateway. So I'm calling it the active route. There is the other route. It's possible that traffic can come here, but it's not, the routing configuration is not, I've not advertised my routes as such. So this is a standby route, not currently advertised. So all traffic comes to the active gateway, but because the servers in the cluster are in a distributed redundant configuration, they are all going to solve the problem. The active gateway will essentially distribute the requests to multiple servers within the cluster. So the cluster itself, this is the cluster, that is spread across both the data centers. So in that sense, data center BE is also contributing to the capacity of the cluster. It's just not directly receiving traffic from the standby gateway. It's receiving it at the active gateway, and the active gateway is distributing it to the multiple servers in the cluster. So that is why I'm calling it an active standby network distributed redundancy model. The difference between this and the active-active model is only that I am in the network also using ECMP. Along with routing, I'm advertising both the routes to the rest of the network. And if both the routes turn out to be equal cost routes, and if the internet uses ECMP, then traffic will, if possible, I'm not saying it will equally get distributed. Unless there's a network load balancer, it may not get equally distributed, but there is likelihood that some traffic lands up here, some traffic lands up on the other gateway. So both gateways in this configuration are acting as active gateways. and they can, either of them can receive the traffic and do the distribution within the cluster. So this is network level distributed redundancy in the sense that the traffic, the network throughput or the capacity of the cluster is being increased by having redundancy or redundant servers in the network. So that's distributed redundancy used for cluster cluster driven applications. Now, what is the requirement that we have from a networking perspective in this case? And we are not going to look at any particular cluster middleware or software, but in general, if you look at vendors who provide cluster software, most of them uh, kind of treat all the servers in the cluster as being connected over a layer 2 network. The cluster is typically treated as a local area network. You don't see it like a wide area network, right? You think of the cluster as a set of co-located server machines, as if they were all in a single local area network. So most cluster vendor software assumes that all these servers in the cluster will have layer 2 interconnection between them. They will be connected over a layer 2 network. And in this case, when I am in fact not having all the data, all the servers in the same local area network, but I'm distributing them across data centers, the cluster software doesn't know that. So the cluster software still expects that these server machines within the service cluster, all of them within the service cluster, they should have what? They should have layer 2 network connectivity. Okay, so it should appear to the cluster software that these servers in the service cluster are connected over a layer 2 network, even if they span across multiple data centers. Now, what is the commonality or similarity that you see in this kind of a configuration with a simple configuration that we were discussing in the last class when it came to single site data centers? There, our data centers were replaced with physical servers. Actually, not replaced, but I'm just drawing an analogy. I had physical servers, and both physical servers had multiple virtual machines implemented. And my requirement was that two virtual machines spread across two physical servers, when they form a service network, a overlay service network, and I want a layer 2 network to be created between those two VMs, I was able to do it. Okay? Irrespective of how the underlay network was connecting these two physical servers. And we know now that a data center network is an IP network, it's a layer 3 network, and that's where NVO3 comes in. But we saw that the overlay network doesn't care about the underlay network. All it sees is layer 2 connectivity between the VMs in the overlay network, and I have protocols and methods, especially the tunneling method, which I can use to create that effect of having a layer 2 network connecting these VMs, even though those VMs are on distinct physical servers. Now, all that we've done in this diagram is what? We've extended that even further. That physical server is not a single physical server, but many physical servers within the primary data center and many physical servers within the second data center. All of them, either directly or as VMs running on those physical servers, need to be defined to be part of the service cluster. So once again, I'm just creating an overlay network that appears to be having layer 2 connectivity, but underneath there is an IP network that connects not only the primary data center servers amongst themselves, but the two data centers to each other. Correct? So I still have an IP-based underlay network over which I can create a sense of having an overlay network, which is layer 2 network across the data centers. How? We just see what protocols come in handy. But I'm just trying to map this to what we learned in single site, and it's only an extension of what we saw there. So geographical redundancy is not any more different, except that we are now saying that, okay, I'm extending the previous example itself. I'm still saying that I have this network redundancy. two primary data centers, A and B, one with active gateway, the other with a standby gateway, or maybe active. Actually, this is active configuration. So I picked up the second diagram from here. And alongside that, what I've also done is I have brought in a third data center C, which is a remote data center. It's in some distant geographical site. So both of these could be, let's say, in Bangalore site A, Bangalore site B, and this could be in Delhi NCR. Okay. So the third one that we've now introduced is a geographically distant and redundant data center. So what I'm saying is that I can I can merge the two together. I can have active data centers running in the same city like we have on the previous slide. And in the active configuration, if I also, so if I, on the previous slide, I said if I don't have a load balancer, then some traffic lands here, some traffic lands there, depending upon the network conditions and which route is considered to be a lower cost route. But if both are equal cost routes and I have a load balancer in the network, then the traffic will get load balanced to both the active gateways. Right? So these are my active data centers. But in addition to those active data centers, I can configure a remote redundant data center, which is like a geographically redundant backup data center for the two active data centers. So why do I need this? I may need this in order to tackle natural disasters and still enable business continuity. So if Bangalore sees some kind of a power outage for that the entire city has, then both the active data centers will stop operation. Both the redundancy is gone. Right? I'm no longer able to load share between the two because both go down as soon as the power outage hit. But so that the complete service doesn't go down, I have a data center running in Delhi, which is able to come up and then take over some of the services of the failed data center. Okay. So yeah, you're right, Arup, when you say that the data center B is the near distributed redundant database, the C is the far geographically distant data center. So this is where it comes in handy. If a fault occurs in the two active data centers due to natural disasters, an earthquake, a fire incident, fire would affect one side, but let's say power outage, it's more likely. Then the remote DR can quickly recover the data, bring up the applications, and it can resume normal service operations in some time, and therefore take over some of the traffic load. There will be not a complete outage. Yes, some reduction in capacity, service capacity, but it does come up. So when I have a geographically redundant use case, the requirement for networking becomes there. So see, we already saw that between the service cluster, there is layer 2 connectivity. Right? That's what we saw. Between the service cluster, there was layer 2 connectivity. Now, in this diagram, I've also introduced the database tier. Okay, so which was not there on the previous slide, if you remember. We didn't have the database tier, we just had the service cluster. So this cluster, as we talked on in the last slide, has layer 2 connectivity requirements. All servers appear as if they are part of a single layer 2 network. But the database is a separate tier. It can be configured as a separate subnet. This could be a separate subnet. So the servers in the service layer, in the cluster service layer, when they have to access the database, because the database could be considered to be configured in a separate subnet, what do I need? I need layer 3 communication between the servers in the cluster and the database in another subnet. Okay. So layer 3 communication will be needed Typically, when I have two primary data centers in this active-active configuration, not both the databases will be active. That doesn't make sense. So one of the databases will be active. The other database in the primary data center will be marked as standby, which means it's doing active data replication. But only one of the database is considered active. That's for consistency in the service. And I can't allow these servers to talk to this database and these servers to talk to this. They have to talk to the same database so that data consistency can be maintained. The second database is in active replication, data replication mode, but it's still a standby database. So there will be layer 3 communication here. There is layer 3 communication across data centers also. So this is cross data center L3 communication between the servers in the cluster and the database. This is cross data center L2 communication. This is L3 communication. So we need both. We need across data center an overlay network that can be seen as a layer 2 network or a network that is layer 3. And these could be separate VPCs also. This could be one VPC, another. We saw in the last class that I can have inter VPC traffic configured. And that typically goes as layer 3 traffic. What I also need is, of course, I said local backup replication of the database, but also remote data backup. So the remote geographical data center is completely acting as a standby. Even the database is configured as standby. It's doing remote data backup. So this is also communication, traffic on the data center network, inter-site data center network. That's the third kind of traffic which enables databases to synchronize amongst themselves locally between near data centers and remotely across far data centers, remote data backups as well. So before I summarize all the requirements, let's also look at the final use case, the distributed cloudification architecture. Okay, Jyoti has a question. L3 means routing based connectivity. Yes. So L3 means I'm using the IP addresses to send and receive traffic. The server talks to a database using IP address and vice versa. So routing comes into picture. Traffic is routed using IP addresses rather than forwarded using MAC addresses. Okay, so the fourth use case is the distributed cloudification, where we are saying the need for multi-site data centers, and all of these sites are actually active mode. Okay, is because I want to take my services closer to my subscribers, thereby ensuring lower latency and improved user experience and so on. So I have in typically these kind of architectures, I generally have a central data center, but I also have what I call as edge data centers, and these are spread across the globe. I am taking these data centers closer to my subscribers. I typically call them the edge data center. And all the central data centers and the edge data centers will also be connected via an intermediate IP network. In this, we are calling it the data center interconnect backbone. It's a network that connects the central data center to the edge data center. The users, they can of course still reach out to the central data center to get their service, but typically they'll be directed to the edge data centers because edge data centers are closer to them. They'll get better experience, lower latency. So this is another fourth use case of having multi-site data centers. Again, depending upon your deployment model, how have you deployed service A across the central data center and the edge data centers? How is service C deployed? Right? You may require across the data centers layer 2 connectivity because maybe service A is deployed as a layer 2 network, or as layer 3 service, maybe service C sees itself as a layer 3 network. So both layer 2, layer 3 connectivity will be required across the multi-site data center. So, okay, I'll come back to this. Let me first summarize. Okay. So if I summarize the requirements that I have from a multi-site data center network, I mean, we are just interested in networking requirements. We have a multi-site data center environment what are my networking requirements for such a multi-site data center environment? So we saw the first requirement is we need the ability to be able to create layer 2 networking across data centers. I should be able to create overlay networks that can communicate across data centers as if they were part of a L2 network. So that's the first requirement we saw. Right? For example, VMs within the VPC communicating at layer 2. We saw this already happens in single site. But there, all our VMs within the VPC were in a single data center. Now we are saying the VPC could cross multiple data centers. That's the first example we saw. Web tier on data center 1, app tier on data center 2, database tier on data center 3. The same VPC that implements a very large web application could spread, the VMs in that VPC could spread across multi data centers. I still have the same requirement. The VMs should be able to communicate at layer 2, irrespective of whether they are in a single data center or across data centers. That's the first requirement I have. The second we saw is layer 3, service interworking across subnets that are distributed across multi-site data centers should be possible. Right? So VPCs need to be able to communicate across amongst each other. I have one VPC on one data center, another VPC on another data center. I want these two VPCs to communicate. One of the VPCs could be implementing the service cluster. The other VPC could be implementing the database layer. And the service cluster needs to talk to the database layer. There are two subnets. So I need layer 3 connectivity between them across data centers. Right? So that's second requirement that we have. The third, which we saw in the geographical redundancy case, was the need for data synchronization and backup, which is more of a storage interconnection network that I need to be created in a multi-site data center environment. So these are predominantly the three requirements we have. How do we meet them? I'll come to them in a moment, but since the order, for some reason I have this ordering of the slides. Let me first take an example of this, one example of a multi-site data center network. I just needed one example to cover all these four deployment use cases. I picked it from distributed cloudification architecture because it's the most common multi-site data center network that we all see. The content delivery network, YouTube, Netflix, right? Any content delivery network is typically implemented as a multi-site data center network. So it's one of the perfect examples that all of us are exposed to, at least as users, where a multi-site data center network comes into picture. Right? So actually, you can look at CDN as a special DCN. Okay, a content delivery network as a special case of a data center network. And what is special about this data center network is it is generally a multi-site data center network. Okay? So content delivery networks are actually special types of networks where the focus is towards content delivery, YouTube videos, even music content. Right? So any form of content needs to be delivered to the subscribers, and the network enables distribution of that content. So as I said, a simple content delivery network can be implemented as a data center network. But we know that when you look at the requirements for let's say Netflix or YouTube, for a service like YouTube or for a service like Netflix, I cannot implement the content delivery network as a single site data center because there are challenges in having a single massive data center. It becomes a single point of failure. If that data center was to go down, my Netflix service across the globe will go down. So it's a single point of failure. The second challenge is that if I set up this massive data center in US West, location. Serving customers in India, Netflix subscribers in India, will lead to very high latency. And the experience that subscribers in India will have will not be good. So, content delivery networks are a perfect example of multi-site data center network. I need distributed data centers across the globe which can work together in the form of, as we saw over here, distributed. They're following the distributed cloudification architecture. For me as a customer, as a user, I'm connecting to the cloud. This is Netflix or YouTube cloud. I connect to the cloud. I don't care which edge data center I'm connecting to. I'm connecting to the Netflix cloud service. But it's a distributed cloudification architecture. There are multiple data centers inside the Netflix district cloudified content delivery network. So that's one example where you will, content delivery networks are one example where you use multi-site data. Now, before data centers became before multi-site data centers became very common, and you still had, in some form, maybe not YouTube or Netflix's, but you still had content delivery networks even way back in late 1990s or early 2000s. You had content delivery networks. What form of content delivery networks did we have? So let's say I wanted to download a patch for my operating system, or I wanted to download a piece of software. So I went to the website www.abc.com, downloading a software. As soon as I click on the download link for that software, this, for good experience, typically the organization ABC had deployed this their FTP servers across the globe. So now FTP can be seen as offering certain content. FTP server, sorry. FTP is a protocol, and FTP server can be seen as a content server. It's offering certain content. Now, even way back in 1990s and 2000, I had this distributed model of content delivery where I would set up my FTP servers across the globe and call them as mirror sites. How many people have come across this term? I know you're all new generation, but and this may not be something that is you may be familiar with today, but anybody in the class who's come across the term mirror sites or used mirror sites a decade or so ago? Yeah, Ravi says yes. So at least somebody knows this concept. So the, yeah, Arun says yes. Okay. So this concept of having distributed content delivery networks is not YouTube innovation or Netflix innovation. Jyoti says yes. So a lot of you have seen this. It's something that existed many decades earlier also. A couple of decades earlier also we had this idea. But there, what would we do? We would set up FTP servers across the globe, calling them mirror sites. When a subscriber would go to www.abc.com and click on, yeah, it was an exact replica of the primary data center. When I click on downloading a piece of software, it would rather open up a web page showing me a list of all the mirror sites. And it will expect me to decide which is the closest to me to actually pick up that site, click, go to that site, and then download my server. So I had control. It will not make intelligent decision on behalf of me. Rather, it's not like Netflix of today. I go to Netflix, I don't even know where the content is getting downloaded from. Netflix takes care of it. They decide what is the best source to give me the data. But when mirror sites existed, this wasn't the idea. The idea was more to throw up a web page of all links to all mirror sites. Let the subscriber choose. And so I would typically pick up Singapore location. India wasn't typically a hub at that point in time, but we would pick up Singapore as a mirror site to download the content, thinking it's still in Asia Pacific, it's closer. The content download will happen faster than picking up a server in US. So distributed approaches like mirror sites, proxy caches, where proxy cache is what? Something that your organizations use. You set up a web proxy in your enterprise network, and let's say you've asked your employees to undergo a training program. It's let's say prevention of sexual harassment, something that every organization wants their employees to do, or cyber security ramp up training that also organizations ask you to do. What happens? You are actually going to the internet to access the content for that training program. But because so many subscribers in the same network are doing it, all employees are doing it, the proxy web server will cache the content and to later employee service it from a local cache. We call it proxy caching. Arup has something on the chat. HP and NetApp and many more enterprises asked to upload logs in their FTP sites for debugging of the products. Correct. Yes. So all these multi-site mirror sites have been there for various purposes, not just content delivery, but also, yeah, as Arup has mentioned, for subscribers to be able to upload logs to enable or help with debugging purposes. Mirror sites, distributed approaches have existed. And the other example I've just taken is the example of proxy cache. So when you have a proxy cache, isn't it like a distributed cloudification architecture? The content, oops, let me delete this. Yeah. So let's say the original content is here in the central data center. And think of this edge data center as the enterprise network, organization network. And the service B that you see over here is actually a proxy cache. It's a web proxy. So when subscribers from the enterprise access the content gets downloaded and provided to this user. The next user comes in, tries to access it. The content has already been cached by the web proxy. It can directly service the next user. So it improves the experience of the subsequent users by using a concept called proxy caching. But essentially, use of proxy caches converts the architecture into a distributed cloudification architecture. These proxy caches become servers for content delivery. So it is like a distributed content delivery network. So various ways in the past also, it's not new, but in decades back, we've always had this distributed approaches. The difference is when we look at modern content delivery networks, like the ones of YouTube's and Netflix's, one, the number of servers have grown phenomenally. Now you have huge number of servers that are distributed across multiple geographically distributed locations because the service has become so popular. I don't have a number, but I'm sure Netflix has its data centers across the globe. And what these content delivery networks are now doing is they are making it seamless for you. You don't choose the best server. They decide what is the best server to offer you content to maximize your user experience. Okay? So how do they set up this content delivery network? What are the approaches? Where should I place my content delivery network servers? Eventually, these are all content servers. Where do I place my content servers? How do I set up my content delivery network? How should I make it seamless for the subscribers? This is all that content delivery networks think about, or that's their design strategy. So content delivery network, if I have to set up a content delivery network, of course, I can set up my own private network like AWS does. AWS will have data centers across the globe, and AWS will have its own connectivity network connecting all these multi-site data center networks together. That's what AWS boasts of. And we have across 170 locations across the globe, the data centers, and all our data centers are connected via our own private communication links across continent, undersea cables. Within the same continent, we have our own communication fiber cables laid out. They have their own network. Larger players can do that. But a smaller player will still rely on the internet because the internet is the public connectivity network across the globe. So if I have to create a content delivery network using the internet as an underlay network, correct? The internet is the underlay network. I have to create my overlay content delivery network. So this is what we saw earlier is the multi-tier internet architecture. I had introduced this slide during the network fundamentals classes, where I said users are connected to access ISPs. They take service from local ISPs. Those ISPs connect to regional ISPs. Regional ISPs connect to tier 1 ISPs. Tier 1 ISPs form the backbone of the internet along with some larger regional ISPs. And essentially, content providers like Google and all, their data centers are connected to the rest of the internet via their data center networks. And so this is what I showed you in that Google YouTube video. Google data center is connected to the rest of the internet. And that's how we access YouTube content. But is it a single mammoth huge data center that Google has in one site? No. What we see here in this diagram is actually just their central data center. It's not the edge data center. It's the central data center, which is kind of the it's the central repository of all content. But we know that if Google were to service all subscribers across the globe from this central data center alone, our experience of accessing YouTube would go very bad. So what we need is Google servers, content servers, placed across the globe to service the users locally. And that actually brings us to the problem of where do I place these content servers? In this whole internet architecture, which is a multi-tier internet architecture, where should I be placing my content delivery network servers? So there are placement strategies that they look at. Where should I be placing? And there are predominantly two strategies. One is called an enter deep strategy. Enter deep strategy is something that larger players often do. They will say, I have a very large subscriber base spread across the globe. And in order for me to be able to give all of them good experience, I will have to follow the enter deep strategy, which means I go right down to the level of access ISPs. I make contracts with them. I tell them, I want my content server to be part of your ISP network. This is how I'm creating my edge data center. So in this slide, when we said service A is deployed in an edge data center, this could be a content server deployed in an ISP network, right? Serving the local users. And that's what we are calling as the enter deep strategy. I'm going deep into the internet, to the edge of the internet, and placing my content servers there. So what is the challenge with this approach? The challenge is it requires me to go down to the level of access ISPs, have multiple contracts with all of them, deploy my content servers at every access ISP network, manage those content servers. So it is a lot of work. It's like creating hundreds of edge data centers. So what is the benefit? It gives the best possible user experience to the subscribers. The other strategy is bring home strategy. These are terms that we use in CDN networks. Enter deep strategy, bring home strategy. So I'm bringing the content closer home. This is my central data center. And rather than going too deep to access ISPs, I rather tie up with some large regional ISPs, and then I have contracts with them to set up my content servers and many content servers in those regional ISP networks. So if regional ISP network, let's say the entire northern region is serviced by Airtel. I'm just taking a hypothetical example. So Airtel will have its ISP network spread across Himachal Pradesh, Haryana, Punjab, Uttar Pradesh, and Google will have a multi-city tie-up with them, saying, "I'll set up one data center in Haryana, one in um, uh, Chandigarh, one in Delhi, NCR, and then all of them will be connected, and they are all part of the regional ISPs network." So what have I done? I've reduced the number of ISPs I'm creating a contract with. I've reduced the number of data centers that I'm creating by bringing them more home. The latency, of course, will be more than having edge data centers. So usually content service providers use a mix of the two strategies, depending upon how my subscriber base is. So if I am Netflix and I know that I have lot of users in the US of a lot of subscribers in India, I would probably go enter deep into those locations. But if I look at the entire continent of Africa and I say maybe not so many subscribers at a country level, but together the continent has sufficient number of subscribers, I'll use a bring home strategy. There have one server have one content delivery server network serving the entire continent. So usually you will use a mix of bring home and enter deep to cater to depending upon your subscriber base. Now, once you placed your servers, you've set something up which looks like this. You have a central data center, you have multiple edge data centers set up. Some of these edge data centers are enter deep, some of them are bring home, but they are all edge data. I mean, let's not use edge, they are not central, but secondary data centers that I've set up. And the backbone which connects all of them is the internet. In this case, in AWS case, it will be a private network that they have. But in other cases, it could be the internet. So now that I've set up my data center, multi-site data center, the next challenge with the next thing that we said is user experience. How do I automatically service my subscribers without them having to select a particular mirror site? Right? So that's where the server selection strategy comes in. I've already placed my servers across the globe. Which server should I select to cater to a user? Right? The simplest strategy which is used in content delivery networks, you could have made it out anyway, is the geographical proximity to the client. So somebody tries to access my content, I actually use their IP address to determine their geographic location, and I service them from a data center that is closest to their geographical location. Right? So that's called the approach. The strategy is using geographical proximity. But is that the best? Maybe not, because it's possible that when the entire set of subscribers in India are accessing Netflix content, the India data center may be overloaded. But because everybody is sleeping in US, it's night time there or actually sleeping time there, the entire data center in US may be underloaded. So geographical proximity reduces latency in terms of the network latency to reach the data center. But the data center servers may be overloaded. So the overall end-to-end latency may still be higher from a geographically close by data center. So the other method that data center content delivery network service providers use is based on the current traffic condition. I periodically measure my real-time delay and loss metrics between my server clusters and the clients who are requesting for service. And based on these real-time measurements of delay and loss, I decide which is the best network to service my clients, my subscribers. So this actually is where, again, you will see the last topic in our course, which is all about observability, network observability. This is one example of why observability is so important. I'm observing my network. I'm making periodic real-time measurements of delay, loss, experienced by my subscribers when they are being serviced by different service clusters. This is observability. I observe my network and I use that to decide which is the best network to service them from. The third approach is to use something called IP Anycast. Right? This is a simpler approach. It doesn't require a lot of observability. And this could be a best possible approach because I'm observing the network and making the best decisions based on real-time delay and loss measurements. But if I just want to keep it very simple, I can actually use a technique called IP Anycast. What is Anycast? So Anycast is an approach where I assign the same IP address to multiple clusters. So I say the Netflix content can be accessed from IP address x.y.z.a. And instead of having this IP address assigned to just one server, I assign it to all the API, the gateway servers. You remember that network level DR, active gateways. I assign the same IP address x.y.z.a to all the active gateways across the data centers. Now, what will happen? See, every data center is advertising reachability information using routing protocols to the rest of the internet. So every data center will advertise reachability to IP address x.y.z.a using a particular path, assuming that we are using BGP for external advertisement. So what is BGP? BGP is a path vector protocol. It will advertise reachability to a network prefix, something like x.y.z.star, and then say it's reachable via me. So I am the next hop, and the path, AS path, is it goes via this. So every data center will advertise it. This reachability to the same network prefix. The information will spread across the globe. What will routers in the internet use, or what will users use? Naturally, as we learned, routing protocols converge to use the closest path or the optimum path to reach a particular network prefix as determined by the routing protocol. So what am I doing with the IP Anycast? So the term Anycast really means I've used the same IP address to assign to every server in the cluster. All of them advertise the same IP address as reachable from them. And users will naturally get routed via the BGP protocol to the data center, which is closest as determined by the routing protocol. So I'm not making any assessment of the geographical proximity, but I'm letting the routing protocol look at the network conditions, current network conditions, and decide what is the closest cluster to reach out to. This is another approach that content delivery networks use, IP Anycast. Of course, the best is you'll be able to give the best experience to your subscribers if you build it over using observability. Gautam has a question. How IP Anycast differs from geographical proximity? IP Anycast may take Indian subscriber even to the US. If it feels that the US clusters are at that point in time, the path takes a least congested or fastest path to reach them. It could go anywhere. It's not geographical. Geographical means via physical proximity, meters, kilometers. With Anycast, it's not physical or proximity in distance. It's more proximity in terms of the routing protocols, assessment of the network path, the real communication network path. Okay, so and plus the fact, Gautam, that in geographical proximity, I had to build certain logic. I had to first look at the user's IP address and then determine which is the closest cluster serving it. So I had to determine the region and then identify. IP Anycast, I don't have to do anything. I'm just blindly banking on the routing protocols to do it for me. So as a content delivery service provider, I don't have to build in any logic. Okay, Yuvraj has an interesting question. So India versus Pakistan, cricket match. The event has a huge surge in subscriber base. Which of these techniques is used? That will vary, Yuvraj, content delivery service provider to another. Hotstar may say I use option 2. I use observability. I observe my network and I redirect my users based on which is the best network to service them today. A smaller network like Geo would say, okay, now Geo Hotstar is just one, but earlier, let's say Hotstar was separate, Geo might have said, I don't have that capability to have active observance of my network. I'll just go with IP Anycast. Hmm? So it depends. It depends service provider to service provider. Most of them will actually be taking service from somebody. So AWS provides its own content delivery network service. It's a managed service that AWS has because, see, what does AWS have? AWS already has these edge data centers across the globe. So AWS has a service called, I'm not sure how many of you have heard of this, CloudFront. It's called AWS CloudFront. It's a managed service that AWS offers you. You just provide the content. AWS will decide which of its CloudFront servers, based on different data centers, should the service get deployed on, and then which is the closest to cater to a subscriber. AWS CloudFront is offering you a CDN service which you can use as a service provider. You don't have to build your own content delivery network on your own. Similarly, you've heard the name of Akamai. Akamai is a similar service. If I want my content to be delivered over a distributed cloudified architecture, I'll go to Akamai. I will become their subscriber. I will give them content and they take care of the rest of it. So there are already service providers who provide me this distributed cloudification service. AWS CloudFront is one example. Okay, Jyoti asked, what about multicast, sir? What about it, Jyoti? Not able to follow the question. Uh, Multicast is one to many. So it's more like what we are doing right now, Teams meeting. I am broadcasting a slide and speaking. Audio and content is being multicasted from me to all of you. That's different from a content delivery network. Content delivery network is more video on demand. Different people are seeing different content based on their demand. Yes, of course, India versus Pakistan match, it can be seen as a multicast service as well. So there are approaches to create what we call as delay bounded, least cost, multicast tree generation over the internet. I say this because this is very old, 1999 or 2000. I published a research paper on this topic. Got published in one of the HIPC conferences, high performance computing conferences, which talked about what your question is, Jyoti. Can I create a delay bounded, low cost, multicasting tree path from a single content server to multiple subscribers across the globe to cater to scenarios like a single content delivery server, multi-user distribution? Yes, so there are things, and it's not new. Now, as I said, I published an approach, an algorithm to build this kind of a delay bounded least cost multicast tree in year 2000. I think it was HIPC 2000 where it got published. Okay, so yes, content different service providers will use some of these approaches. This is what sets them apart from the other. Akamai, they will not disclose what they are doing, but they have these kind of methods to give better user experience. So sometimes you would say Netflix is often better than, just an example, I'm not saying it is. I'm saying if you feel Netflix is better than using Geo Hotstar, what is the difference? The difference in some of the techniques that they are using in delivering you content. Okay, it could be bring home versus enter deep. It could be that they are using some innovative approach for creating a delay bound multicast tree to do a India versus Pakistan broadcast. So yeah, these are USPs which all these content deliveries net service providers employ. That's what sets them apart from the others. Okay, so all I wanted to do was take one example which is very close to everybody to show that why are multi-site data centers so much required. Okay? Because when I say there are huge modern applications which may not be possible to service from one data center, they require multiple data centers to get service. You might say, sir, this looks a little far-fetched. Is the application so huge that it requires two data centers worth of infrastructure to service it? But this is a very practical example. A content delivery network requires multiple data centers. Okay, so I wanted to take one very practical example of a multi-site data center and then say, yes, this is why you need multi-site data centers. You have applications like these. Content delivery is an application which gets serviced via multi-site data centers. Okay, so back to our networking requirements and how they get fulfilled. Okay. Oh, by the way, I've already passed the 1 hour boundary. This I can stop here. It's a logical point before I get into how do we implement each of these requirements. We've formulated the requirements. We've identified these are the three requirements from a networking perspective when it comes to multi-site. How do I implement it? What protocols? So that's the next part of my class today. So we can take a break now. A 5 minute break, 11:41 by my watch. We'll start at 11:46. Okay, I think we should get back. Yeah. So let's look at how we will achieve all these requirements. And we are going to be, from this perspective of this course, we are more going to be focused on requirement 1 and 2. Requirement 3 is something that is more related to storage area networks. How do you create a storage area network or over an IP based underlying network in order to enable quick and fast data synchronization and backup? In this program that you're doing MTech in cloud computing, going forward in subsequent semesters, at some point in time, there's an elective that talks about this topic. It's a course on DSTN, data storage technology and networks. So there, the data storage networks is what is going to be covered. But very quickly, while this is not something we've been covering in our course, requirement 3 is typically implemented by creating a storage interconnection network that is often implemented using DWDM techniques, dense wavelength division multiplexing, or bare optical cables. So you basically set up direct physical links across the data centers using DWDM or optic cables. And this has the advantage that you can actually get exclusive channels where you can fully meet the latency requirements required for data center, redundant data center synchronization. So it will provide you a high bandwidth, low latency path for traffic exchange between data centers. If you don't want to use or set up your own uh, uh, DWDM or optic fibers cables between the data centers, you can also use an IP network like the internet. And there are techniques that allow you data transmission of multiple protocols over a storage area network that is created on top of a IP based underlying network. So you have SAN over IP, flexible storage area network over IP services. Uh, so generally, this requirement is met by creating a IP storage area network or a bare metal fiber optic cable storage area network, right? So either you use set up your own bare optical fibers or you use an IP network to create a storage area network. But storage area network is a separate topic, which we of course are not covering in this course. But that gets covered in the DSTN elective course if you are interested in taking that. Right. So the other two requirements, which is L2 networking across data centers and L3 networking across data centers. Now, this is something which, as I was talking a little earlier, is nothing but an extrapolation of the requirement that we had within a single site data center. So in a single site data center, the data center network was an underlay network that was IP based. And the overlay network that I wanted to create between virtual server machines or cluster of machines in the form of a VPC was it was possible to create it as a L2 or a L3 network by using a VXLAN tunneling approach. Leaving aside VXLAN, essentially any NVO3 approach can be used to fulfill requirement 1 and requirement 2. Because when we studied NVO3, we said NVO3 is a technology that enables creation of an overlay network. NVO stood for Network Virtualization Overlay. So we were able to create a virtualized overlay network using underlay layer 3 network. So any NVO3 technology, or for that matter, any tunneling technology, any encapsulation and tunneling technology can help me meet requirement 1 and 2. Okay? So if I have to do L2 networking across data centers, I can use a tunneling technology like VPLS. What is VPLS? It's a virtual private LAN service. And remember, I talked about EVPN in the last class, BGP EVPN, where we said you have an intermediate MPLS network and multiple branch offices connected over a service provider's MPLS network by creating a virtual private network via tunneling. So that is what I'm calling now as VPLS, a virtual private LAN service. It's a kind of a VPN that I've set up over a underlay MPLS network. And MPLS generally runs over Ethernet. Right? So we called it the EVPN, Ethernet VPN technology. So typically you have the protocol stack looks like this. You have layer 1, physical layer, PHY. You have Ethernet as the data link layer. You have MPLS, which is neither layer 2 nor layer 3. Typically, it's a sandwiched layer between layer 3 and layer 2. It's called layer 2.5. And then I have IP on top. So MPLS is, as I was telling last time a little bit about last time, it's a label switching approach over a data switch network. So it introduces a concept of circuit switching like functionality on top of an underlying packet switch network, which Ethernet is. So I can use an MPLS network and create a layer 2 tunnel across the two data centers as if they were two branch offices. And this is what we discussed last time, but we did not give it a name. It's called VPLS. It's a virtual private LAN service. It connects multiple Ethernet networks across the public network to enable the Ethernet networks to function as if they were part of a single LAN. This is when we talked about BGP VPN. They were the branch offices, head offices, they were working as a single LAN. So we created a L2 network between them using VPLS service. That's what we talked about last time also. The disadvantage, I mentioned this last time also, is that MPLS is not a public network. The public network is an IP network, internet. Internet is an IP network. It doesn't have, it's a standard IP over Ethernet over PHY network. It doesn't have MPLS. Right? Internet does not use MPLS. So if I want to use MPLS, because MPLS gives me better quality of service, it's like having a circuit switch network created over packet switch. So there are things like resource reservation, traffic switching is faster because it uses a technique of label switching rather than routing. So traffic is switched at the MPLS layer rather than routed at the IP layer. So it's faster. But if I have to use that, I need to go to a private service provider who set up his own MPLS network. And I need to take service from him, likes of Tata Teleservices. I'll have to purchase connectivity service from them in order for me to be able to connect my data centers to each other. So if I want to avoid all that, I just want to use the standard internet, then I can once again fall back to VXLAN, which is my open source, practical, publicly used NVO3 technology. So when I use VTEPs at the edge node, so I have a VTEP here, I have a VTEP at the other point. VTEPs are actually creating tunnels, but they are creating what we call as VXLAN tunnel because they are doing MAC and UDP encapsulation. Right? So VXLAN essentially provides L2 VPN service only, but over a IP network. That's what we saw in the single site data center network. So I can use VXLAN across data centers. At the edge of both my data centers, I can set up VTEPs. I can create a tunnel through the IP network, a VXLAN tunnel using MAC and UDP encapsulation. Okay. So this is a low cost, easy, and something that can work long distance because the internet exists across the globe. If I go to Tata Teleservices for MPLS service, maybe it's restricted only in India. My data center in Bangalore and Delhi could be connected via Tata Teleservices MPLS network. But what about something in US? So IP networks by using internet enable long distance, low cost connection and it's easy expansion. Tomorrow I have a data center in some location where the MPLS service provider is not there. I can still use VXLAN as an option to connect my data center. The disadvantage in this approach is the advantage of the first approach. In the first approach, I said the advantage is because MPLS is a private network crafted over a public network, the underlying network, and it's using label switching, it's faster. Routing is slower. The public network quality is restricted by the best effort service of the internet. So my quality of service is constrained by the public internet, but it's easy from an expansion perspective. Okay, so these are options. There are other options. I can use any other NVO3 technology also, but essentially I need some tunneling technique to carry my layer 2 traffic between the data centers over a layer 3 IP network. Okay, Jyoti has something. Oh, okay. You're just elaborating on what I said. MPLS means office to office WAN connectivity, where VPLS means data center. Yeah, correct. Right. So these are ways I can do it. These are not the only two options, but two of the predominantly common options that exist for setting up a multi-site data center networking requirement. Same way, if I have to create L3 networking over data centers, what do I need? I need to create a L3 VPN. In the previous case, I had to create a L2 VPN. Here, I have to create a L3 VPN. I have to take L3 traffic and tunnel it through an underlying L3 network. So MPLS even supports L3 VPN. Right? I can take layer 3 traffic, tunnel it through the MPLS network, creating a L3 VPN. It's the same thing as on the previous slide, but because it's L3 traffic tunneled, I'm calling it a L3 VPN. In the previous case, it was L2 frames getting tunneled through the MPLS network. So we were calling it a L2 VPN. And the second option, once again, is to use VXLAN because VXLAN also allows me to do both. It allows me to take L2 or L3 traffic and tunnel it via the VXLAN tunnels. So in general, if I'm using VXLAN as the protocol within my data centers, it only makes sense to use the same technology and the same protocol even between my data center so that it becomes my data center interconnect solution as well. And that is why predominantly you will see VXLAN being the recommended protocol or the most used DCI technology in multi-site data centers because everybody wants to use the same protocol inside and outside. Okay? Why worry about two different? So when I'm using VTAPs and VXLAN tunneling within my data center, why not use the same across my data centers as well? So if I look at my multi-site data center service model, what am I trying to show in this picture? I'm just trying to show you what you would be learning in a course like cloud computing and what I am teaching you in a course like network fundamentals for cloud. I am always operating at this layer, the data bearer layer, the actual network layer where the data actually gets carried. A course like cloud computing is actually showing you AWS consoles and showing you how you set up a multi-site data center on using an AWS console. I'm not sure if they've done it. I'm assuming it will be done or it would have been done by now. So if you go to AWS console, by the way, AWS calls these as availability zones. Is that a term everybody's familiar with? The term availability zone, has that been talked about in cloud computing course? Yes, no? Yes, okay, thank you, Meghna. Right? So what is an availability zone? As AWS calls it an availability zone, it's a second site. It's a different data center. So when I use the AWS console in a course like cloud computing, when you are using the AWS console, you are setting up an overlay network. You are creating your own tenant specific network. AWS calls it the VPC, virtual private cloud. You can set up the VPC, and this VPC can have multiple subnets. Let's say in this model, I have subnet 1 and subnet 2. And I've said that subnet 1 infrastructure I want to be set up on availability zone 1, which could be, let's say, the US East data center, and subnet 2 I want on the US West data center, which is availability zone 2. This is what I do on the AWS console. And this is what tenants typically see. This is the service model. This is what AWS will show to you on their console page. We call it the service model. You create a VPC, create two subnets within it, deploy one subnet on one availability zone, the second subnet on the second availability zone. But what is really happening underneath is what you're learning in this course. What is happening underneath? The VPC is actually two VPCs, VPC1, which is subnet 1, VPC2, which is subnet 2. They are actually getting set up across two data centers. And between these two VPCs, you may require layer 2 connectivity or layer 3 connectivity. So our course is teaching you how do you get this L3 and L2 interconnection going between the VPC that is spread across two availability zones. And that was my first use case today. I had a VPC having web tier, app tier, database tier. It was spread across three data centers. So that is what you're doing on the AWS console. Underneath, this is the availability zone 1 data center, DC1. This is data center 2. They have their own class network fabric. That fabric, which is the underlay network, uses VXLAN to create the overlay networks. And what we just learned today is that even this layer 2, layer 3 interconnection that I set up across fabrics, across two different data centers, that is also using VXLAN protocol. So essentially, okay, I'll come back to this. I am not, I'm actually skipping these slides because you've already said that this is something you've learned in cloud computing course. What is a VPC? What is a subnet? How does Amazon allow you to create a VPC? How do you define a VPC in AWS? You define its sub-constituents like a subnet mask, which availability zone it should get mapped to. Okay? So I don't want to cover it because this is something your course in cloud computing should be covering. Okay. Yeah, I mean, I am going to give you this in slides. So what is VPC? It's a tenant virtual network. It's your network that you're creating in the cloud platform in AWS cloud. You have a set of IP addresses via which you can access this network, this VPC. This network could itself consist of multiple subnets. Okay? You could create security groups within the network. You could connect this VPC to the rest of the internet. Okay? So it's like a physical network of your enterprise, but set up on the cloud. Okay? So this is what it will look like actually. This is your VPC that you've set up. It could be spanning. So this is your first example that I had taken. It's spanning across two data centers. Amazon calls it availability zones, AZ1, AZ2. Availability zone 1, availability zone 2. This is a little different than my architecture, though. In my architecture, web tier was all on one availability zone. Here they have some EC2 machines running as web tier, some other EC2 machines running as app tier, a database running as the database tier in one availability zone, the same replicated in another availability zone. So this architecture is also possible. Right? But this is one subnet. Okay, let me blow it up a little. I'm not sure if you can see it. Yeah. So let me blow one of them first. So this is one architecture. This is subnet 1. I have created a subnet within my VPC on availability zone 1, and I'm saying all the VMs, virtual machines, running the web tier are part of subnet 1. And they communicate amongst themselves using private IP addresses. All these VMs which are part of the app tier, they are in subnet 3. Right? All the VMs where all the databases in my availability zone 1, they are part of subnet 5. So it could be a distributed database. Right? I'm not restricting. Similarly, subnet 2, 4, and 6 are set up on the second availability zone for the web tier, app tier, and database services. Right? And how do I connect them? I want them to be connected to the external internet network. So I set up an internal gateway. This is like my router, which connects to the external network, but it's like a BGP router because it's also advertising public routes outside, public IP addresses, reachability outside. So it's a gateway. So what is it advertising outside? Some public IP addresses it's advertising to the external network using BGP protocol. This is like a V router, virtual router that I've set up, a BGP router. So it's advertising these public IP addresses. Remember the active configuration, I had some virtual IP addresses. Those are being advertised to the external network. So traffic will come from the external network via this gateway for these IP addresses to this gateway. The gateway might give it to an elastic load balancer. The load balancer may distribute it across the web tier instances, EC2 instances across the two availability zones. So that's the elastic load balancer. Right? You can have internal routing set up between these subnets so that web tier traffic can go to the app tier traffic can go to the database tier. So that's the within the VPC you are setting up routing protocol. Right? So this is what we discussed last class. What can I do in my overlay network? I can use I can use OSPF, I can use RIP, I can use these protocols to set up routing between my subnets. I can even use static routing also. If it's a smaller network, I can use static routing. Okay? So all of this is possible just like I do in a physical network, I'm doing it in a VPC. This is what is a virtual network that you create on the cloud. So that should, Yuvraj, you requested in brief, I try to do it in brief. Okay? But if you want more, ask your instructor in cloud computing course to talk more about it. But this is in brief what a VPC is. So what is really happening behind the scenes to set up this VPC? I am not sure if I talked about it earlier, but if this is the kind of network that I want to set up, do I have to? So in cloud computing course, you might be doing it via the AWS console, physically setting it up. There might be some lab activities where you're setting this kind of a network up via a AWS console. But normally I don't do it manually. What do? I use a concept called infrastructure as a code. IaaC. How many people familiar with this? What I do is I create a script file. This could be a Terraform script. I could use Ansible. These are tools that I can use to write a script file. It's like writing code. I generate a script file and I say I need to set up a VPC. But within that VPC, I need 6 subnets 1 to 6. Each subnet has these IP addresses. These VMs are part of this subnet. So what am I doing? I'm defining the entire structure as code file. And as a script file, this is what I mean by infrastructure as a code. So I write what I need, how I need to have this diagram. I'm just putting it in text as in code. I provide that Terraform or Ansible script file to the orchestrator. Every cloud has a orchestrator, which will take in this script file, this code file, and deploy the entire infrastructure, the entire VPC for you automated in the backend. So generally what do? We write Terraform scripts. I say this is the VPC I want to set up. I put everything in a script file. I give that script file to an orchestrator. The orchestrator reads that code, reads the script file, and sets up the VPC for me. So yes, I can do it from the console manually, but if I want to automate it, I will write a script file, give it to the orchestrator will set it up for me. And what is the orchestrator doing at the back end? Remember the NFV architecture I had shown you? It talks to the VMM. The VMM was the virtual machine manager in the NFV architecture. It talks to the VMM. It talks to the VMM to spawn VNFs, virtual network functions like vRouters or vSwitches, or it talks to the VMM to set up VMs on the physical server pool. So what is this? This is the infrastructure layer, physical infrastructure. This is your data center servers, which are connected via the interconnection fabric, the class topology. So the orchestrator uses the NFV architecture. So I'm also now trying to tie up everything together. Now that we've covered all topics, I'm tying it up together. You know SDN, you know NFV. We've talked about single site data center networks. Today we've also covered multi-site. This slide ties it up all together. So when I give a script file to an orchestrator saying set up a VPC for me, it will read the script file, parse through it, talk to the VMM, spawn the VNFs that are required to set up that infrastructure. So I need a gateway to be spawned. I need a router to be spawned, which will connect all these instances, or I need multiple routers, vRouters to be spawned. I talk to the VMM. I spawn those VNF and those VM machines on the server infrastructure that I have, but I also have to interconnect them. How do I interconnect them? I talk to the SDN controller. The SDN controller helps me set up those interconnects by setting up the flow tables. So this is completely centralized override in the overlay network. So in the overlay network, I generally use SDN to set up the flow rules for the overlay network. In the V routers and the V switches, I use SDN. So that's why I said your V switches in the hypervisor, the next class I'll actually talk about them. They are also SDN enabled. The SDN controller can configure the flow rules within them. Okay. So how are the data paths eventually getting set up? Eventually, I will have these VMs running on physical servers. On some leaf switches, they get connected to the rest of the fabric gateway via VXLAN tunnels. Okay? And then if the traffic has to flow across the data center, this is cross data center VXLAN tunnel. And then within the data center N, there'll again be a VXLAN tunnel. And that's how the traffic reaches the destination VM. So if I'm sending traffic from this VM to this VM across two data centers, there'll be three VXLAN tunnels that will get set up. One within Fabric 1, one within Fabric N, and one across the backbone, the data center interconnect backbone. Okay. The VXLAN control plane could all be BGP EVPN that we learned last class. So this is how, when you set up a VPC like this on the Amazon Cloud console, underneath the orchestrator, the NFV framework, VMMs, SDN controller, they are all working together, controlling the real infrastructure in the data center to set up a forwarding path like this for you. So that all happens on the fly. Okay. So this is your multi-data center networking architecture. Okay. Now, the rest of the slides, I'm not going to go into a lot of detail. All that they're showing is that you can have, like we saw in the Facebook data center, you can have hierarchical data center. There could be multiple fabrics rather than a single fabric, and then a super spine connecting all these fabrics together. So in that case, when you have multiple fabrics, you have an IP network between the fabrics itself. And that's the data center network architecture. So VXLAN still works. You will still have end-to-end VXLAN within the data center that can be set up. across fabrics. Okay? Over the underlay data center network, IP network. And then you can have the internet, which is this IP network being used to connect across data center. So whether it's a single fabric or multiple hierarchical fabrics like in the Facebook network, I'm still working with VXLAN tunnels to create the overlay network connectivity. See, when I draw overlay network, I just say this VM, this VM, this VM, they should all be part of the same L2 network. Whereas in reality, this VM could be on data center 2, this VM could be on data center 1, fabric 1. And this VM could be on data center 1, fabric 2. All it translates to is to underlying in the underlay network set up the VXLAN tunnels. So remember, I made one statement at start of the course. I said the underlay network and the overlay network operate in a complete disjoint manner. The architecture, the topology of the underlying network, whether it's hierarchical fabric like this, like the Facebook, or a single fabric like this, doesn't make a difference to how I set up the overlay network. I can define my overlay network like this. And this can be set up on a data center underneath, which could be single fabric, multi-fabric. Okay? The orchestrator takes care of it by setting up the right tunnels, VXLAN tunnels between the endpoints. So all that we are doing is we are setting up end-to-end VXLAN tunnels across fabrics, within fabrics, across data centers. That's what we are doing. Right? So there's a VXLAN tunnel here, there's a VXLAN tunnel over the internet, there's a VXLAN tunnel within data center too. So this is what I essentially wanted to cover today. Yeah, I mean, this slide is more to say that AWS actually has a lot of ways in which external network connections can be made to your VPC. And this basically from the perspective of hybrid cloud. So I have a VPC set up on AWS, but I need it to connect externally to, let's say, my on-prem network, on-premise network, creating a hybrid cloud. So AWS provides you a lot of network connectivity options. It provides you what we call as a peering, what they call as a peering connection. A peering connection is an internal connection within your network. Right? So you can create a VPC peering connection between two VPCs within your own private network to enable you to route traffic between them privately. So it is a construct, a networking construct that AWS offers to you, which allows your VPCs to talk to each other as if they were part of the same network, even though they are across two different data centers. So AWS calls it a peering connection. They will, when you set up a peering connection between two VPCs, it automatically sets up all the VXLAN tunnels and everything that is required underneath to enable these VPCs to talk to each other. So that's called a peering connection. When you want to connect your on-cloud VPC to your on-prem network, this diagram, they have a networking appliance called a transit gateway. So a transit gateway can connect both your VPCs. The private subnets can directly be connected via the transit gateway to your on-prem servers. Right? So it's like creating a virtual private network between your on-prem network and your on-cloud network. It also has a concept of site-to-site VPN, which you can set up. Okay? So this is a site-to-site VPN. So you can use a direct connect VPN gateway to create a site-to-site VPN between your on-cloud and on-prem network. So there are a lot of different network appliances that AWS offers: transit gateways, peering connections, direct connect VPN gateways. These are methods that it allows provides to connect the VPC that you're making on cloud to external networks which could exist in your own enterprise network, on-prem network. And of course, we just saw this. I can create internet gateways to connect to the rest of the internet. So this is what you see, or this is what the terms that you would be hearing in the cloud computing course. But beneath everything is what we learned in this course. It's all about creating tunnels. It's all about creating at times, I mean, sometimes it's just tunnels, sometimes it's secure tunnels, encrypted traffic within the tunnels, like this case, VPN. It's not just a tunnel, but it's also encryption afterwards in the site-to-site VPN. Okay, so this is what I had about data center network. Okay? So we've covered what three parts of our course: network fundamentals part, which was the first 5 or 6 classes, then the SDN and NFV, which was actually enabling technologies part, and then the data center network part, where to quite an extent we've also covered the virtual overlay networks because they're tied together in cloud computing. The next class, we will completely get into the layer above. We're done with the physical layer. We're done with the data center network. We will now jump into the overlay network. We'll say, okay, now that I have a VPC, a overlay virtual network setup, what is a V router? What is a V switch? How do VMs communicate amongst each other? But more importantly, what are the performance challenges when it comes to traffic forwarding or switching in an overlay network? What are methods to improve performance in the overlay network? What are other ways in which virtual networks can get set up? So we have talked about VMs, virtual machines. But what about containers? Today we deploy a lot of applications as containerized applications. Are they also a part of the overlay virtual network? Yes. Containers are eventually being deployed on underlying physical servers. So containers also talk to other VMs, containers talk to other containers. How is all of this networking in the overlay network, in the virtual networks happening? This is what we will cover in the next class. So I have a question for you people. Has the concept of containers been covered in cloud computing course? Do you know what a container is? Okay, yes, good. That's good. Because I always try to bring this topic in alignment with the MTech cloud computing course, so that once you should know what containers are before I actually come to the topic of container networking. So yes, next time we'll do all of this. We'll talk about networking in the virtual network layer. What is VM networking? What is a vSwitch? What is the internal architecture of a vSwitch? Where are the performance challenges in a vSwitch, a virtual switch? How can I do away or improve the performance of a virtual switch? What is container networking? How do containers talk to each other? This is all in the virtual network space. So this is what we will cover next class. That will be class number 14. Class number 15, we will talk about network security, both underlay network, the data center network, and the overlay network, the virtual network. What are techniques that are used to securing these networks? That's the part about network security in data in cloud networks. And class 16, which is the last class, we will talk about observability. Both underlay and overlay networks, how does observability help me? Why is it important? So that's the last class. So this is how, now that we have clarity of what we've covered and what classes remain, this is how I'm going to cover the remaining topics in the next 3 classes. So next class is all about virtual networking, virtual layer networking. The following is all about network security. The last class is all about network observability. Okay. So thank you everyone for joining in. We are ending the class 4 minutes early today. I will see you next Sunday again with a brand new topic where we move above the data center network and more into the virtual network layers. Thank you and see you next week. Bye bye.